Hello everyone, let's continue our foundation engineering class. We started previously the chapter number 3, shallow foundation, the ultimate bearing capacity of shallow foundation. I think we did just introduction last time, and this time we will go for the theory of the Terzaghi's bearing capacity theory for shallow foundation. Okay, so this This video will not be very long. It will be it also kind of introduction of bearing capacity of shallow foundation. So, uh, who is Terzaghi? Terzaghi is a French guy. In 1943, he developed the first time comprehensive theory to allow engineers to evaluate the ultimate bearing capacity of shallow foundation. Okay, graph one. So the first comprehensive theory. Okay. So according to him, a shallow foundation is foundation that the depth is no no more than the width of the foundation. Okay. The embedment depth of the foundation itself cannot be larger than B, the width of the foundation itself, according to Terzaghi's theory. Okay. So as we can see, an illustration here, this figure showing the illustration, we can see B here, okay, and DF here. So according to his definition, DF is less or equal to B, okay? It cannot be more than B. So we will come back on this detail on this figure later. But after a few years, some researchers also show that, okay, even up to 3 or 4 times the B, even if the DF is up to 3 or 4 times B, it can still be considered as shallow foundation. Okay, so can be classified as shallow foundation. So DF can be higher than B, up to 4 times. It okay, it's still shallow foundation. Okay, so about this figure now, let's try to understand it. Okay, so for continuous or strip foundation, okay, it means the foundation is very long compared to the width. Okay, the ratio where the width to length ratio approach to 0, it means it very long footing. The length is much longer compared to the width of the foundation. Okay, another way you can see, if you take B divided by the length, the total length of the foundation, it will be approaching 0. Okay, for this kind of foundation, Terzaghi is suggesting that the failure surface in the soil at the ultimate load. I think we did define what is ultimate load in the previous video. So I hope it was okay. It was understood and I don't need to come back on this again. Okay. So at the failure means at ultimate ultimate load, the failure surface in the soil resembles to this. It looks like this. And if you remember in our previous video, this is what we call general shear failure, actually. Okay, general shear failure. So according to him, for strip footing, when the ultimate load is reached, the failure in the ground, will look like this. Okay, so what do we have here? So as I said, general shear failure, what we did last time, it looked like general shear failure. Okay, so soil above this, can you see this dashed line, which is at the same level as the base of the foundation? Okay, all the soil above this line is considered as like surcharge. Okay, so this soil can be easily replaced by its own weight. It means Q, this Q is unit weight multiplied by DF, the depth of the foundation. Okay, that can be replaced by, that soil can be replaced by its own weight. Okay, so this is just a reminder what we did last time for general shear failure. This is how it the load settlement curve, how it is presented, and this was this is general shear failure. Okay, and that was punching, and this was local shear failure. Okay, we define all these three type of failures last time. So in the Terzaghi's assumption, the general shear failure is happening for strip footing. Okay, so the failure zone beneath the foundation can be divided in three parts. Okay, this is the foundation. Beneath the foundation, you can divide this failure zone in three parts. Okay, we will describe these three parts soon. The first part, triangular zone, A, C, D. You can see A here, C here, and D here. This is the first part. Look like triangle, okay? Which is immediately under the foundation, okay? The second part is like these two, A, D, F. Okay, it is same here, C, E, or C, D, E. These are same, okay? So we call them like second, okay? And we can see that this arc, this curve, like a D, E, and D, F closing, like logarithmic spiral. But anyway, we have these two zones also, because each zone, each failure zone has its own like characteristics. And the third one, or the third ones, are these. This part means AFH, and this one CEG. Okay, this one third part. Okay, so and these third part are like ranking passive zone. Okay, for the CAD, this first part, okay, you can see like a punch, and ACD, this angle, you can see this angle and this angle, these two angles, alpha, CAD, this one, and ACD, this angle. These are assumed to be equivalent to the soil frictional angle, phi. Okay. For example, if you're dealing with sand, that is easy. Okay. So this alpha are equivalent to the phi, the friction angle of the soil. Okay. And the soil above the base replaced by the sharp charge. This one, we explained this already. The shear resistance of the soil along the failure surfaces. This, for example, G2I. We have G here, I here. Okay. We just suppose that it will extend like this linearly, but actually we can also neglect this. Okay. It means by replacing the soil above the footing base by its own weight, we are assuming that the shearing resistance of this soil doesn't contribute to the bearing capacity, which is actually not strictly right, but this is just assumption according to Terzaghi. Okay, the shear resistance along this, okay, H, J, and G, I, they're not participating. Okay, this is the meaning of replacing, or this is what it means by replacing this soil by its own weight, by just the surcharge. So using the now equilibrium, like limit equilibrium, because it is like some forces, we want to make equilibrium of this, for example, this part, this block of soil. So using limit equilibrium, Terzaghi expressed the ultimate bearing capacity in this form. Okay, QU, ultimate bearing capacity, equal to C prime NC plus Q NQ plus half of gamma BN gamma. Okay, so this is the equation of how to obtain ultimate bearing capacity of uh, strip footing, strip foundation, only strip foundation. And we are going to see what is the meaning of the NC, NQ, okay? B, I think B you know already. It is just this dimension, the width of the foundation, okay? And C is also known, it's just cohesion of the soil, okay? And Q is here already, the surcharge. So if you check closely, and also, sorry, gamma is the unit weight of the soil, okay? Then if you check closely, you will see that this part of the formula is the contribution of the cohesion of the soil, okay? Cohesion of the soil. And this part, where you see the Q, is the contribution of the weight of the soil above, okay? Be careful, sometimes you will be given unit like two different soil. This zone has, for example, 18 as unit weight, and this one has 20, for example, as unit weight. The one you will use will be this one, both, okay? The weight of the soil. And gamma here is the contribution of this, the weight of this soil this time. The soil beneath the foundation this time. Okay? So we have here three part: contribution of the cohesion, contribution of the surcharge, contribution of the unit weight. Okay. So this cohesion is the cohesion of the soil beneath here. This cohesion, this unit weight is the unit weight of the soil beneath the foundation. But this surcharge, this contribution is the contribution of the soil above this. Okay. This foundation. So be careful when you have layered ground. Okay, if you have, for example, this above the base of the footing is, for example, loose, or like not loose, but like lighter than this one, different characteristic. So you have to consider that. I think we will discuss this in when we will start doing like applications, some exercises. Okay, already explained. So C prime is cohesion of soil, gamma is unit weight of soil, Q is this one, the surcharge. Okay, now what is NC, NQ, N gamma? These are what we are calling here bearing capacity factors. Okay, they have no dimension and they are function only of the soil friction angle. Okay, so it means these three factors, these bearing capacity factors, can be determined only by using the friction angle of the soil. Okay, so this is for this video, for this part of this chapter, this is the key part. This is the thing you need to understand. Okay, but of course we will add some things, because so far we are just talking about strip footing or continuous footing. Okay, but how about circular footing or square footing? Okay, so this, I put back the formula here. Okay, and we continue. For strip footing, this is what we have. Okay, so bearing capacity factors, we said NC, NQ, and gamma. Those are defined by using the frictional angle of the soil. Okay, so for NC, for example, this is the formula you have to use. Okay, if you check in this equation, the only unknown is phi, the frictional angle of soil. Okay, this is simplified form is here. Okay, but in this simplified form, you have NQ. So it means you have to find NQ first before getting. This is NC, okay? And NQ itself, which is this one here, is defined here. I hope you understand this equation. It means you can obtain the NC from NQ also. And NQ, which is defined here. But the only thing you need is phi, okay? And N gamma is like this. This N gamma. So you can choose several value of phi, frictional angle of soil, and calculate by yourself in an Excel file and obtain several value of NC, NQ, and gamma. These are according to Terzaghi. Okay, so this KPY is just passive pressure coefficient. So when we use like phi, okay, we did something for you, you can use this value, okay, from 0. When phi prime is 0, the friction angle is 0 to 50, which is covering the value, reasonable value of friction angle of soil. Okay, up to 50, I think. So you can check, verify it by yourself. When phi is 0, what will be NC, NQ, and gamma? Okay, this table is obtained using these three equations. Okay, but just changing the value of phi, you can calculate. If you want, you can calculate by yourself. Okay, so let's keep these equations here, NC, NQ, and gamma. And this, remember, it's for strip footing. This equation is for strip footing, continuous footing. So what about now for square and circular foundation? How do we estimate this, the bearing capacity in that case? Okay, for square foundation, okay, means we have four equal side. In that case, you add this coefficient, and you see the difference between this one and this one. It is 1.3 added. 1.3. This is what we call shape factor. Shape factor. Okay. This is strip footing. This is for square footing. 1.3. Okay. NQ is same. This middle part is same as strip footing. And here we have another coefficient changing. Instead of 0.5, it became 0.4. Okay. 1 divided by 2 is 0.5. Okay. So here it's 0.4. Okay. So the only thing that is changing is this coefficient. 1.3, 0.4. Okay. And since it is square, B is equal to the dimension of each side of the foundation because it is square. But for circular one, what is changing? You can see 1.3. Here also is 1.3. But here it is changing to 0.3. So here 0.5, 0.4, 0.3. These are shape factor, but we will come back on these later also. Okay. But in this case, the circular foundation, circular footing, B, as you can see, we don't have the width or side of foundation here. It's circular. In that case, B will be just the diameter of the foundation. Okay. B is equivalent to the diameter of the foundation. So now we have three occasions for strip continuous footing, square foundation, and circular foundation. Okay. So remember that these are when we have general shear failure. These three for general shear failure. Okay. So for foundation that exhibit local shear failure mode in soil, we talked about this local shear failure previously. When then we have local shear failure, we need to bring some modification to this equation. It cannot be same anymore. So Terzaghi suggested the following modification. Okay. This is just explanation of the different type of failure we explained last time. General, local, and punching failure. Okay. So we are talking about this one, local shear failure. Okay. And we explained last time in which condition this local failure happen. Okay. So here is what we need. Okay. For local shear failure, this equation above here becomes this one. So you can see by yourself the modification. For strip footing, this one becomes like this. What is changing is only here. 2/3 added here. That's all. Okay. Here, for square foundation, we have this. You can compare it with this one. Okay. For circular foundation, we have this. Compare it to this one. Okay. This is in case of local shear failure mode in the soil. Okay. And last time we explained when the local shear failure happened in the soil. Please remember that. Okay. So some people are just applying one formula. For example, this one for strip footing, this one for square foundation, but it's not actually right. Okay. You need to know like what type of soil you are dealing with. So if you know the type of soil, then you can understand, okay, what type of failure you can expect. Is it general shear failure or local shear failure. Then after that, you can select the appropriate equation, appropriate formula. Okay, this is normally what you should do. Okay, so you can see the difference here. Here, for general shear failure, we have NC, NQ, N gamma. Okay, but for this local shear failure, we have NC prime, NQ prime, N gamma prime. They are not same. Okay, the bearing capacity factors for local shear failure are not same as those with general shear failure. Okay, these NC prime, NQ prime, N gamma prime are modified bearing capacity factor that can be calculated using this one, the bearing capacity factor using these. Okay, by replacing the phi, the frictional angle phi is this time replaced by this one. Okay, it is tangent minus 1. Okay, for this one. So by calculating, you calculate first this angle, this new modified angle from the friction angle in case of that you would use for general shear failure, and then you can obtain a new angle. And then by doing that, you can replace this now in these equations and calculate what you will obtain n c prime, n q prime, and gamma prime. Okay, so we have here this table showing n c prime, n q prime, and gamma prime. Okay, from phi prime from 0 to 50. So in case of local shear failure, use this table. Okay, for this one. It is not same as this. I hope everything is understood. So later you will see that there are many other modifications to this Terzaghi's general equation to consider the inclination of the foundation or the inclination of the load or the shape factor. We already discussed this. Okay, so we will come back on this modification later in this program. Okay, so thank you very much for your time. That will be all for this time, this video. So see you very soon. Thank you very much.